Yeah, I'm ready. I'm refreshing the page just to
Okay,
make
okay.
just to check.
I'm going live. Make sure the sound
Yeah,
is
we're live.
okay. You check? I think we're good.
Yep, we're good.
All right. Hello, everyone, and welcome to today's brand new episode of Corecast. I am your host, Tim.
And this is Sahil. Welcome everybody to a brand new exciting episode of Workcast. We're back after a little bit of a break, but we're back with I hopefully what you would find an interesting topic. So before we get started, a few logistical things. If you haven't already, do join our Discord channel. And if you're watching on YouTube, where we tried to do this rather at 5 p.m. Pacific, 8 p.m. Eastern every Tuesday. Do ask us questions during the episode. We can get to them as well. So without further ado, Tim, let's get to it. So we've been talking a lot about time over the past few episodes, like the different directions or different arrows of time, rather, like anthropic, electromagnetic, psychological, mentioned briefly cosmological and whatnot. And I'm sure we'll like talk more about that during this episode. And so these different ways of thinking about time. But I guess like one natural question, and then of course going backwards in time. So check out those previous episodes if you haven't already. We talked more in depth about that. But this kind of talking about sort of like the end. I don't know. A lot of people talk about this, the quote unquote end state of the universe, this thing called the heat death. And so before we, go into what we want to discuss about it, Tim, it might be helpful to the audience to explain kind of like the logical steps of, first of all, what is a heat death and how do we get to that? Like, how do people arrive at that conclusion? So just really break it down.
Yeah, I think the heat death originally was this idea was kind of initiated when people were studying what we call thermodynamics. It's really taking a statistical view of the universe. It's to thinking about as opposed to thinking of the universe as particles moving around with 100% certainty. Is trying to approximate a universe into probabilities and into categories and whatnot. And what people observe is that as time goes on, the behaviors of systems on Earth tend to be for lack of a better word, I guess, more and more kind of less controllable. Like for example, if you put gas molecules in the corner of a room, and then you unleash that box, kind of the gas molecules escapes, and there's almost no way to put them back. So these behavior tend to be very generic, and there's this concept of irreversibility. It seems like once the physical interactions occur, it becomes irreversible. Like what in a very analogous sense, like once you know for example, once you use let's say gas to drive your car, and those gas turn into exhaust, the energy kind of becomes wasted, and those can be quantified rigorously mathematically. And the conclusion seems to be that the more this happens as time goes on, the more kind of wasteful energy you created, and there's still sort of this wastefulness that can be encapsulated in a concept called entropy, which keeps increasing. And ultimately, if you kind of project this forward, you might come to the conclusion that at some point the universe will exhaust all of the possibility to do interesting things and come to what we know as the heat death, meaning that there's nothing more that can be done about the universe, at least practically. And that has been popularized. I think I don't even know where, but I think it seems like everyone knows something about it. It's like this is the ultimate end of the universe. But the question is that really the end? What does modern physics have to say about it? So
Yeah. I guess like can you walk us through maybe like more, I guess more from like uh I'm thinking how to describe this. More from like what we would if we lived long enough to see this, what would we see? Like if you take the current state of the universe, there's lots of interesting things happening. But like what does it mean that like this like energy is becoming like wasteful? I thought I knew that energy was conserved. So why is it like different versus one form versus the other? And how would it look if I lived like till the quote unquote this end of the universe heat death or whatever. whatever you want to call it. Like, what would that process look like?
Yeah. So so energy is conserved, but actually it's not exactly conserved because of the expansion of the universe. But let's ignore
Mhm.
that for now, okay? For our purpose, is conserved to that extent. So energy is conserved, but um, when I say it becomes less useful, is because things that get scrambled. Like heat energy is not very useful. Like you can't just power a turbine just because it's hot out. That does not work, right? And in
Mhm.
terms of the universe, um, this directly affects the things we do on Earth. But we're talking about a much grander scale, much larger scale, right? Like at some point, our sun is going to burn out of fuel, basically, and then
Mhm.
one of the interesting things to work with is going to go to red giant. It's going to consume the Earth, but that's going to happen to basically all the stars in the universe. It's going to burn out at some point. The fuel is
Mhm.
not infinite, right? And when that burns out, um, the stars might become dim. It might become. I mean, there's a lot of astrophysical phenomenon. It might turn into like a useless star, white dwarf, whatever you call it. And then
Mhm.
what's left is you're going to have black holes running around. So at the center of every galaxy, there's a black hole. So it will continue to eat stuff, accumulate mass, right? And as stars die, they merge, they might get reignited again, and eventually those also will burn off. All the fuel ultimately will burn off. And all that's left is black hole consuming matter. And at some point in the really, really, really far future, like it's not orders of magnitude of the age of the universe, right? Like I don't even know, eons and eons and eons later, we might just end up with just black holes and maybe some radiation around, kind of like the heat exhaust. But even black holes are not forever because Stephen Hawking and many others calculated that black holes themselves can radiate, evaporate, right? So all that was consuming the black hole also generates waste in some sense. And when those occur, the decay product of the black holes will become radiation. So now at some point, the universe is just filled with nothing but radiation. There's not even black holes in it. So that now it becomes a super duper boring universe. It's just a heat bath of radiation, and maybe the universe will continue to expand and whatnot. So that's kind
Mhm.
of practically, I guess, with a more modern knowledge, what a cosmological heat death will look like. Like it's literally like a bath of
Mhm.
useless radiation that we can't do much with it at all.
I see. But aren't there like certain particles that we believe could like, I don't know, loosely speaking, live forever in quotes, like electrons and stuff like that? Like what
Yeah,
would
but
happen to those?
in the face of black holes, those will still eventually get consumed by some black holes, and then
Mhm.
when I mean, even though these we believe to be conserved, whatever electric charge is conserved, whatever. But
Uh-huh.
once they get eaten in the black hole, that will also decay into particles of light, right? And I
So,
guess, mhm.
mhm. So one question about that is like the universe is expanding. Eventually, you're going to get like these super clusters of galaxies that are just like too far away to communicate with each other. At least, they'd be
Mhm.
proceeding faster than the speed of light. And so you'll pretty much have like maybe just one black hole in this like region of space that's like reachable by light to each other. So are you saying like how do you like I guess how do you know that like there won't be some like set of electrons or like protons or just other particles that are really far away from like from these black holes, so it won't be fully just all like photons and whatnot, right?
I mean, it could be plausible. I mean, there could be a
Mm-hmm.
few stragglers, I imagine.
Mm-hmm.
Um, but the majority of the stuff will be
Mm-hmm.
consumed by these supermassive black holes.
I see.
So sure, there could be a few stragglers, but the majority of the universe is pretty, pretty uninteresting. Even if you add in those stragglers, like there's not much they can do, you
Mm-hmm.
know.
I see. Okay, just wanted to get some more clarity on that. Yeah, no, that makes sense. So I guess like okay, so this is more of a like classical type of approach to figuring out how the universe will evolve and eventually reaches this like this finality, this really boring state where like basically it's like dead, and just this like this heat bath in this background that's like actually very cold. But actually, why is it called heat, like heat death? It's on probably be very cold relative for us, right?
Yeah, it should be very cold. I mean, the temperature of outer space is pretty damn close to absolute zero. And yeah, in an expanding
Mhm.
universe, it will get colder and colder. I think the heat death, the notion of heat death is a little bit historical because that concept comes from things like heat engine and like um, thinking of the universe statistically. So I think that's why the name stuck.
Mhm.
Um, so I mean it's heat related because it becomes kind of statistical. It becomes everything is kind of sort of scrambled up in an unrecognizable fashion. So,
Gotcha, gotcha. And then last question before we go on to what we wanted to discuss in this particular conversation is like, because this is a statistical notion, isn't there a chance, like classically, that like these particles could like assemble themselves, like a bunch of photons that are like just this heat bath of photons could like collide together, and like a star could form, and then that could produce like planets and stuff like that? Or
yeah,
like, I'm talking purely classically. Yeah.
yeah. I mean, there is some chance, right? I mean, there's this theorem we talk about, this recurrence, even
Hmm.
classically. Like like there could be really rare instances that particles could
Hmm.
happen, just come together.
Hmm.
But in classical physics, there is still a limit. So,
Hmm.
for example, if there's not enough energy for things to happen,
Hmm.
it's just kind of stuck, right? Like
Hmm.
when two particles don't have couldn't pass certain barriers to do something, um, it just a reaction could not happen, right?
I see. I
And,
see.
and, and generally, in the heat death scenario, most of the interaction that releases energy has already been done, right? We're
Hmm.
talking about time that's like eternal. This is like eternal time, a really, really, really long time, right? So all the leftover processes will generally require energy, and in the classical framework, you're just not gonna get it, right?
Hmm.
It's almost like your bank account is completely empty. Like you're in serious credit card debt. Like there just is
Yeah.
no hope for the universe at this point. At least conventionally, there is no hope. The universe has no hope. It's kind of like
I
hopeless
see.
ending.
I see. Is there, okay, last question is, can we give the audience a sense of time? Like, is it 10 to the 10 to 100 years? Like, how long would you like say this time scale is? Just
Oh yeah,
rough order of magnitude.
yeah, it's probably exponentially long, like 10, maybe 10 to the 10 to the 10, something like that. Um, I mean, when we talk about these numbers, it's not even precise anymore. I mean, you can probably calculate it to some extent,
Uh-huh.
but these are just unimaginable time scale. So
Mhm. Fair enough. All right then. So let's come to the crux of why we wanted to do this episode, because when you and I were talking about this, this is actually not the end of the story. In fact, this makes the universe seem really, really like uninteresting, but it's more interesting, as you were telling me. So can we now bring in what element is the story missing? That's like essentially very crucial.
yeah, and that to some extent that's the interesting bit. The universe, it turns out, it's a little less grim than we thought. I mean, we follow up this credit card debt analogy, right? Like even though the universe is totally in debt, it's got no credit, it's got no money to do anything. It's completely starved of whatever it wants to do. Well, there's a trick up the universe sleeve is that it can still borrow more. It can, I don't know, go into bankruptcy mode or whatever. And the way to do it is through quantum physics, right? The beauty of quantum physics is that it can almost do the impossible. It has the ability to tunnel, basically, right? And that's why
Mhm.
particles, for example, can go through walls if you test your experiments well enough. Like for example, if you have a beam of electrons, let's say you try to shoot through concrete. Classically, that's just not happening, right? But in quantum physics, if the wall, actually, it doesn't matter what the thickness of the wall is, but if the wall is thin enough, there's a reasonable chance the electron could just go through, like actually, but not destroy the concrete wall, can just tunnel through to the other side, right? And even when the wall is really thick, it still has a chance, although a lot smaller, exponentially smaller, but there just is still a chance to tunnel. So now that brings an interesting possibility. Well, certainly, the universe is out of options now. It seems all hope is lost. But with the power of quantum physics, all these quantum bits coming together, really rarely, occasionally, it could almost borrow sort of the necessary energy to do interesting things. And all of a sudden, like a phoenix rising back out from the ashes of heat death, it could come back alive a second time. Interesting things could happen once again.
Huh. How would that work? Like, I mean, classically, I understand the picture of like if it doesn't have enough energy, but what do you mean borrow energy? Like, I thought there's like a fixed amount of energy, or I mean, not fixed, but like I don't know, just like yeah, where can it borrow energy from? Or can you explain that a bit more?
Yeah, I think we need to understand the conservation of energy a little bit better,
Okay.
right? Classically, we say that the total energy is conserved, right? You have a fixed amount. Either whatever you do, the sum is better got to add up, right? This is almost like a cashier that's keeping tabs of everything, right? Very precise. Quantum
Mhm.
mechanically, the laws of conservation is a little more vague. It only says that the quantum mechanical average needs to be conserved, right? Basically tells them to do that,
Mhm.
telling you that, hey, there's a lot of fluctuation in quantum physics. As long as the fluctuation overall adds up, then it's okay. So the quantum cashier is a little more lenient, right? Like you can borrow energy for a little bit as long as later on you return negative energy, which could
Mhm.
happen, right? At least loosely quantum mechanically speaking. Mathematically, yeah, the vacuum could go through. I mean, mathematically, in quantum physics, we know things could be in sort of like multiple states at the same time, sort of this,
Mhm.
superposition. You can think of it in that way that the universe can be in multiple states of energy, right? It can go into an
Mhm.
energy deficit or an energy excess, right? It could be a linear combination of the two. And some of those paths of excess can explore these interesting options, right? So it's not just like there's one universe. It's almost like there's kind of many, the universe is kind of like had many possibilities, and some of them could just stumble upon something interesting. And that's why, that isn't quite the end yet, because the universe still has this ability endowed by quantum physics to kind of have some fun, kind of poke around and try out different things, even though it's got nothing to work with right now.
Huh. So I guess like I mean this comes back to one of the things we talked about. I guess I'll mention it briefly, but I don't want to dig into exactly what it is, but this notion of like decoherence in the sense where like yeah, there are these different possibilities as you were explaining, but when I like do a measurement, the other possible like say I want to measure an electron, whether it's like flipping a quantum coin, whether it's heads or tails. If I do the measurement and it comes out tails, the possibility of heads is still there, but it's like it's not as easily accessible to us. So in that context, like what do you mean like that there are these other possibilities are like quote unquote exponentially suppressed, right? Like they're
Yeah.
harder to access. So
Yep.
how does that work with what you just said?
Yeah, so indeed they are exponentially suppressed, but keep in mind that we are working with eternity here.
Uh,
Even when something is exponentially small, when you wait an eternity, exponentially small times infinity is still it's still going to happen. So that's a little trick that quantum physics has up its sleeves, right?
mm,
Like
mm.
it's small, but it's not zero. So small number times infinity, infinity still wins.
That's fair. That's fair. I guess then, like, what would this look like? Or I mean, I don't know if "look like" is even the right word, but can you give me some kind of analogy or something to kind of like wrap my arms around this? Like right now, we're talking about possibilities. That seems very abstract. Is there another way I can like think about this?
Yeah, unfortunately, it's a little difficult because we in our world like we don't experience these quantum fluctuations very much because
Mm,
we live in a macroscopic world, and in fact, you can study in the lab. A lot of some of these quantum fluctuation is very small, so you can imagine like a little interesting possibility could pop out, but very quickly just get destroyed again. Kind of like it borrow
mm,
energy, but it return it. So there's this things happening in vacuum, and we can test it out by studying the vacuum in detail,
mm,
and because these processes actually carries energy, and that can be studied and quantified, and that has been validated. But in our everyday lives, yeah, it's not going to be apparent. Like maybe on the top of my hand, there could be some quantum fluctuation here and there, things
mm,
popping out. But on average, I don't see that, right? Because my hand is a large object, right? And these
mm,
tiny fluctuations I don't see. And I and and I mean, don't get me wrong. If the universe is structured in such a way that we go through heat death, and there are quantum fluctuations, a little bit popping in and out. Sure, it's a slightly better than heat death, but still not much better. You see, like it's still
mm.
like a little pop here and there. It's a little more interesting than totally nothing. But look, it's still not much better than heat death, right? Um,
Mm.
so so far, uh, it's not quite the rebirth yet, but there are strong reasons to believe that's not the end of the story either. There is a little
Mm.
bit more to this process.
What does that little bit more mean?
Yeah. So like I said, um, when these little pockets of quantum interesting things, I guess, pop out, you could roughly calculate, what's the size of that, right? What, of this interesting thing happening. Like for example, imagine an electron or an anti-electron pop into existence. Let's say they pop into existence, dance around, evaporate. Okay, so they borrow energy, return energy, nothing happens, right? You can say, well, what's the size of that? Maybe it's super tiny, happens at a really small volume. Um, but if there's a reason why that little pocket of Dan dancing around will be amplified, then this processing will actually be a lot more dramatic, right?
Mm,
And it turns out that we believe that there is, at least in many of the leading theories, and also personally, I would believe that to be true. I think our universe has a way of amplifying those processes. There is a way,
mm.
and that's why, even this quantum version of the heat death, that's probably not the end either. It's gonna be a little better. Like these quantum fluctuations can amplify, and it can be amplified a whole lot.
I see. So you're saying like there's two versions of the heat death. One is classical, where it's just this like boring dilute gas of photons, just nothing exciting happening, just
Hmm.
dead pretty much. And then there's the quantum version of that where it's like, oh, it's dilute gas of photons, but sometimes electrons, positrons will appear. Sometimes these particles will appear, but it's like, nothing much more than that. And then what you're saying now is that you can there's certain there's if you wait long enough, there'll be certain extremely amplified interactions that could produce interesting, I'll use in quotes, stuff that could come up. Is that fair to
Yeah,
say?
yeah, yeah. Basically, the idea is that what if, when this interesting bit pops out, it happens that region of space, as opposed to just collapsing right again. What if there's a natural way for it to expand, for it to get bigger, bigger and bigger and
Mm,
bigger? If that were to happen, then what we'll have what we call bubble nucleations. It's almost like a
mm,
boiling pot of soup. You got little bubbles pop up. Bloop, the bubbles will get bigger and bigger and bigger. Except, of
mm.
course, the universe doesn't have a lid. The fluid doesn't have. It's not like we're not literally talking about water here, right? We're talking about entire universes, and maybe there are pockets
Mm,
of interesting things happening,
mm,
bubbling up, right? And so this is sort of the image that physicists were in imagining. right? Sort of this bubble nucleation processes.
Mm, I see. I see. So could that be said about our universe? Like we could be a bubble that
Yeah,
just popped kind of out of
and
existence
and I
into
think
existence.
so. And I quite think so, because this idea originally comes from, let's backtrack a little bit, comes from the idea of inflation. Inflation is an
Mm-hmm.
idea that says maybe our universe has some propensity to exponentially expand, get bigger and bigger and bigger. Basically, more
Mm,
space gets created. Um, let's not go into the details. It was originally proposed by Alan Guth, and it got
mm,
refined by many other physicists. It's to
mm,
solve other physics problem, which we will not get into, right? And so basically, it's this idea that there are ways for the universe for space itself to get bigger and bigger and bigger, right? And now we've established that actually our universe has the size of the universe is getting bigger at an accelerated rate. We have an accelerated expansion.
mm,
And so that kind of gives a little more credit to this idea. Look, it's not crazy to think that there are ways for space to expand itself. And the
mm,
only requirement for that to happen is what we talked about earlier is there needs to be some sort of tunneling, right? So
mm,
if you have a universe in which, I guess to speak abstractly, it's almost like phases of water. Water can be liquid, gas, solid, right? Okay.
mm,
If our universe has multiple phases where one phase can transition to another, and technically we call these different vacuum structures, but whatever, it's kind of like water, then that means there's a way for bubbles to form, for these bubbles to grow exponentially. And
mm.
then, in a really real sense, our universe could be a little bit like a pot of bubbling, boiling water.
Hmm. Interesting. I guess like how do I think about these bubbles? Like, because when we're talking about quantum fluctuations, we talk about particles popping in out of existence. Is there some like way in which we like a more kind of precise definition of bubble? Is it like I'm just throwing this out there. But my guess probably is not. This is not the answer. But like, is it like, oh, if X electrons appear, X like muons are there, these number of things appear, or like, what does it take to make a bubble? Like if just yeah, like what would that take? Like, how do I know
Yeah,
something is a bubble? Is kind of my question.
yeah, and these are very good questions. And a lot of study on these objects are not very precise. Now, obviously, we don't have a
Mm.
lab to make universes to make the universe bubble up, but we have theoretical tools to think about. What the hell are these bubbles in a universe, right? So,
Mhm.
so in some sense, it's similar to what you described. The universe, there could be bubbles that temporarily get created because of this
Mhm.
quantum just randomness. Quantum
Mhm.
randomness kind of borrow energy from the universe, kind of created these little pockets, right?
Mhm.
And then these little pocket is a physical object, right? Like a water bubble, they have things like surface tension, and the inside has energy. And the question is, when these create out of no pop get created out of nowhere, what is the balance? Is it going to want to expand, or is it going to contract, right? If it, the surface tension will want to contract it, but the expansion of the little universe inside will want to expand, right? So
Mhm.
so the majority of the time, quantum physics might create a bubble that might be too small. There's not enough vacuum
Mhm.
energy inside to make it happen. So
Mhm.
okay, so those bubbles don't do anything, right? But
Mhm.
remember, quantum physics is kind of like this not so precise thing. Occasionally, some bubbles will be created large enough to kind of sustain this reaction.
Mhm.
And when this happens, it's kind of like a new universe gets created. It's almost like a little big bang out of these little
Mhm.
bubbles. The bubble
Mhm.
gets bigger and bigger and bigger and bigger. And this
Mhm.
sounds kind of familiar, right? It's kind of like
Mhm.
the story of the beginning of our universe.
Mhm. That makes sense. I guess would there be any kind of like would it need to contain all the different kinds of fields? Like we discussed in previous episodes, many episodes back, like the inflaton field, gravitons, like would those need to like be in there for it to actually do this? Like, because I mean, I mean, correct me if I'm wrong, but based on my understanding, we strongly believe that like in the early universe, like everything was just like one field, like it's just all one thing, and then eventually, as the universe cooled, it started to split into these different things, different objects. And so I'm wondering, like, is it a similar situation here?
Yeah, and it is indeed pretty similar, right? Like because and at
Mm,
the heat death, kind of all the
mm,
quantum fields sort of quiet down. And remember, quantum fields is sort of this all permeating objects that exist
mm,
not just in our universe, but also in sort of multiverse. I mean, we haven't gone to this multiverse idea, but the multiverse idea is in completely born from this bubble idea, right?
mm,
When all the fields are quiet, and all of a sudden you get a little pocket, that pocket is able to grow, and inside that pocket, certain field that you mentioned, maybe an inflaton field or some other field that carries energy, is able to
mm,
grow. And that looks like a new universe. It's like the new beginning. It's almost like,
mm.
I don't know, one of the Star Wars movies, right? Was
New
that a new
Hope.
beginning? Yeah. And this can
Yeah.
happen everywhere in the universe. There could be bubbles left and right, front and back, top and bottom. And then we get this fantastical picture, that out of the heat death, it's not the end. It's almost the beginning, almost like a fractal-like structures of bubbles here and there, one universe here, universe in a universe, bubbles in bubbles,
Mm,
expanding and kind of in this grand symphony. I mean, it's
mm,
just fantastical picture, right? It's like a
mm,
orchestra of universe being born left and right, and just this web of fractal universe. And
mm.
in a real sense, we might already be in one. Our universe could have been one of these bubbles. Who knows?
That's fair. I guess like I had a question for you, and then I completely dropped it. What can you remind me what we were saying previously? You were talking about bubble universes, and it's escaping me. Yeah, I don't remember what my question was. Uh
Was it the
I,
fractal like structure or the?
yeah, it was I hate when that happens. Like I had a question I wanted to ask you about this, and now yeah, it's totally escaping me. Yeah. I guess maybe like okay, well, another point is we don't see this at this moment because like the time scales that we live on are much too short for any of this to happen. Is that a fair
Yeah,
statement?
yeah, exactly. This is, I don't know, 10 to the 10 to the 10 to the 10. I don't know what time scale that is.
Mm,
And some physicists have been very critical of this idea because it's
mm,
completely not testable, right?
yeah.
Let's say your theory proposes there are bubbles, multiple bubbles of universe. Well, heck, we're never going to be able to see one because, like, if we live in a little
Hmm.
bubble, these bubbles grow at the speed of light. Like, you're never going to
Mm,
catch up to the boundary, unless you're super lucky in some ways, I guess. So people argue whether or not this is science, right? Like,
ah,
does it make sense to think about the multiverse in that way?
mm,
Um, but I mean, I don't know what to tell you. This is sort of the limits, of kind of human knowledge of how we think about
mm,
cosmology and physics. I don't know if
mhm,
there's a good answer, but that's what the mathematical equations would tell you. And this behavior is actually
mhm,
relatively generic. So it's not crazy. It's not crazy, but
mhm.
just not verifiable or falsifiable in some ways.
That is true. So one other question I think this was the question that I was thinking, but different question is like you mentioned earlier about tunneling and tunneling being very important in this process. So like what does tunneling have to do with I mean the notion of like borrowing energy, for instance, or like being able to like yeah, like what does it mean for the universe to like tunnel through something like what is it tunneling through?
Yeah, yeah, yeah. So to be a little more precise, what physicists talk about is sort of these energy landscape, right? That
Mm-hmm.
that uh, th- and we believe that so what is the vacuum? The vacuum can be thought of a kind of like a minimum of energy, because the universe
Hmm.
like to minimize the energy and whatnot.
Hmm.
But and a question arises: what if there isn't just one possible minimum? Maybe there are
Hmm.
multiple, right? So there are multiple possible vacua for the universe to choose. But then the question is, well, how does the
Hmm.
universe choose? And the correct
Wait,
answer.
one
Mhm.
really quick question. So, how does this work with like energy conservation? Because it seems like you talk about minimum energy, which implies that there are different energy levels, but we just talked about it. Shouldn't it just be flat? The energy is conserved, maybe with a few wiggles here and there.
Yeah, well, it doesn't need to be flat. There could be
Mm-hmm.
like many mountains and valleys in this landscape, and it could be
Mm-hmm.
almost infinite. There could be many bazillion different choices, right?
Mm-hmm.
Um, and then the universe will choose. How does the universe choose which one to be in? This is
Mm-hmm.
almost just randomly happening by chance, and in fact, it doesn't just choose. It almost samples all of them at once, right? All the
Mm-hmm.
possibilities are sampled in the landscape of quantum physics. So that's how it's why it's different from classical physics. In classical
Mm-hmm.
physics, if the universe is stuck in one little valley, it's stuck there. It's never going to
Mm-hmm.
escape. But in quantum physics, it kind of samples all of these possible valleys. And when
Mm-hmm.
bubbles form is when, like imagine this patch of universe. I don't know how large it is. Maybe it's got a few million galaxies. Let's say this patch of the universe I have. It might be in one little valley, right? But then quantum physics tells you that, hey, maybe some patch of the universe happens to randomly wander into a different valley, right?
Mm-hmm.
And borrowing energy, meaning that, oh, it can't use, it has to return that energy somehow. It has to annihilate, soon
Mm-hmm.
enough. But before that happens, that bubble might have grown larger now, right? So even
Mm-hmm.
though some of it might annihilate, it could, it's got enough oomph to grow bigger and bigger. And that's even a possibility. Maybe there are infinitely many of these little valley. Maybe the, kind of this mountain ranges of
Mm-hmm.
landscape. It could be infinite. So
Mm-hmm.
so so there could be almost an infinite tunneling. It will never end. Right? There's no deepest valley anywhere. So this is kind of like a way more interesting and dramatic view on what it means for like almost like the universe trying to, I guess, trying to find a minimum, right? In an abstract
Yeah.
way.
Could we think of it like, I'm gonna draw somewhat of a classical picture here, where if I imagine like a bunch of hills, like hills and troughs, and some troughs can be like lower than others, and I imagine the universe is this like, represented as kind of this ball, and if I put it on a hill, it drops down to one of the troughs, but classically it can't like, once it's at the bottom, it can't like go up a hill because that would, that just involve you to have more energy. But quantum mechanically it could like, tunnel through a hill and end up like going downhill on like a trough that's even lower, and that could give like the energy that it could quote unquote borrow. Is that a fair analogy?
Yeah, that's fair. And in some sense, it's a little more dramatic. It's more like the ball has a split personality. It turns into
Oh.
10 different balls. Each of them were able to sample a new different
Mm,
valley, and each of them were able to create a new universes, localized in that valley. And so
mm.
it's way more fantastical. Like we don't just have a ball here. We got some kind of superpower, like like ninja balls, if you like.
That's fair. Ninja balls that can clone itself, or I don't even know. I don't even know if clone is the right word. It's even
Yeah,
more fantastical than that.
it's way more
No,
fantastical.
no clone theorem from quantum mechanics was not clones.
Yeah, that's true.
Um,
Yeah.
yeah. Okay, now I remember my question. So you talked about like with quantum mechanics borrowing energy and paying it back in the sense when like particles get created, and then they immediately annihilate each other after like a very small instant of time. How does that work with this amplification process? Because if we're like this sort of like universe that's created on, you know, loosely speaking, borrowed energy, like how is it going to be paid back? Or like what does that work? Does it ever get paid back, or like, yeah, I just want to understand that
Yeah,
and
yeah.
that.
Yeah, I kind of just use that term loosely because really,
Mhm.
when I say payback, I just mean that because even though energy is not strictly conserved in quantum physics, on average, it needs to conserve, right? So
Mhm.
if there's an energy excess here, there's got to be some deficit somewhere along the line, right?
Mhm.
So maybe there could be energy excess here, and then maybe as it tunnels, there could be an energy deficit afterward to kind of compensate, so it averages out. So
Mm.
so this payback mechanism, it's not like someone borrow and then pay their credit card debt online,
Mhm.
but it's a little bit more abstract. They can pay back kind of like anytime they want, but as long as on average it evens out, it's all good, you know.
That's fair. That's fair. So I realize we're almost at time. Wanted to give you a chance to give any final words to the audience before we part ways.
Yeah, I would say that um, you, you, a lot of people kind of have this depressing picture of the universe, oh, going to hit that, like, and kind of maybe go into this existential crisis, like, oh, what's the point of living anyway? The universe is all heat death at the end, right? But really, quantum physics, give you this fantastical alternative. Like, not only does the universe live on, this could be this could be a multiverse, not just one universe either. It could be like a massive fractal like structures of, it's better than sci-fi movies in some sense, right? Um, and it kind of makes you wonder. At least personally, I wonder. Like certainly after my death, I won't be on this universe for too long, but still, the bits of information I have is preserved, right?
Mhm.
And those maybe carry on to get scrambled up. I might exist in those bits of information could exist in a multiverse, seeing an eternity evolving out with all kinds of interesting things happening. I think that gives you a little, at least it gives me a little bit of comfort, knowing that the eternity, it's a little more interesting than we would hope, I think.
Mhm.
So I think in a real sense, it's poetic, I would say. The end of the
Hmm.
universe, actually, there's no end. It's eternal.
Yeah. So the death of heat death is what we talked about
There is
today.
no heat death and there's no end. It keeps going. So,
Fair enough. Fair enough. Well, on that note, I want to thank you for joining us, and we'll see you next episode, or
yeah.
maybe in the next bubble universe, because there's no end.
Yeah. See you